Hello, 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 it's audible. Yeah, good evening. Okay, okay. That's okay because we have 2 hours. And that's why I've not started yet also because now yeah, it's audible, na? Yeah, the slides is also yeah. Actually, today we'll see generally it's the palladium, ruthenium, some that's basic reagents. Most of the cases, and today we have maybe around 13, 14 slides. So maybe it will go so faster. Yeah, that the first questions we have, that we have iodobenzene, that propagelic alcohol. This one is nothing but propagelic alcohol and iodobenzene. That's this the triple bond alcohol and in presence of that palladium, that had tetrakis triphenylphosphine, that tetrakis triphenylphosphine in copper iodide also. Here copper iodide is also the metal, both metal is that the needed for that reaction. And along with we have that amine that in this reaction we are using for that base and heating. Generally this reaction will do heating, and after that we have that the lithium aluminum hydride. So reducing agent also we need for that reaction. Then what will happen? Do you have anything that that's any idea that what kind of reaction will happen? It's not steel coupling. If it's steel coupling, then we need tin metal. Then we call them the steel coupling. Triple bond is. Do you think that's whether only triple bond is can be reduced? Only that. Suppose if you have a oh, there's someone is joining. Yeah. What do you think? Whether that triple bond will or yeah, triple bond can reduce by lithium aluminum hydride. Suppose you have only that alkyne, that the phenylacetylene. Suppose that you have only phenylacetylene. Whether that triple bond will that reduce by lithium aluminum hydride or not? It won't reduce. But on what condition that it will reduce? I told you maybe that this thing. No, in that case, but at what condition by using that the lithium aluminum hydride that it can be reduced? You can reduce. That told you some for particular type of substrate that it can be reduced. That's if you have any in alpha position, if you have any that hydroxy group or amine group in that particular cases, that it will be possible to reduce. If you have any that the propagelic type, then only that kind of triple bond that that can be possible to reduce. And in that all cases, we'll get the E alkene. That's whatever the alkene will get. But if you do from that linear catalyzed or the other the hydrogenation, in that cases we'll get J alkene. That's the G alkene. In the because whatever that hydrogenation that will occurs from that the same phases. But in this particular cases, that hydride ion will be attached only. After that, it will abstract a proton and you will get your corresponding alkene as a trans alkene. वो उनका as E alkene. Okay. But in this case, what will happen actually? This whatever the coupling will be the coupling between that triple bond, terminal triple bond, and alkyne CH bond. That's whatever carbon sp in hydrogen bond with our aryl halide, the in presence of palladium and copper iodide, and in the amine and heating, that will get our corresponding the coupling product. After that, what will happen? That in this particular cases, for this kind of that propylgenic alcohol, that's the if of that's in alpha position, that if of hydroxy or amine group also, in that particular cases, that we can even reduce alkyne by that the lithium aluminum hydride to their corresponding E alkyne. Okay, but if you use that's our that's any hydrogenation, that's with controlled hydrogenation, then you can reduce from alkyne to the alkyne to alkene through the hydrogenation. But in that cases, you will get that Z alkene. This whatever this one is trans, and you will get in that cases that cis one, that the cis alkene you will get. So that's why the importance of the hydroxyl group in this case is also most important. And the general mechanism what will happen, that's whatever that the palladium, the after leaving of the two triphenyl phosphine, then that you will get that the palladium zero species, that will be our the most reactive species, and after that whatever aryl halide we have, that it undergoes that the oxidative addition reaction, and followed by that we have the copper iodides and amine, and that will be help to our alkyne for that the transmetallation by using that the copper iodide, that will be reacts with our terminal alkyne, and followed by from that the amine, that we have reduced our hydrogen ion, that's HI, and you will get the corresponding the copper the copper metallic alkyne, and that will undergoes with the transmetallation reaction. That's palladium, that species, this species, and you will get your corresponding that the transmetallation. In the last cases, that we have the reductive elimination and leaving our the catalyst as such. That's the active species, that is palladium 08, and the cycle also begins such a way. That's why in that whole cases for the palladium or catalytic other cases, that's we need only that's the mole percent, that like for example catalytic amount of that metal that's we need. That's why this reaction is very useful, that if you put the reaction in very high scale, so you need only that 2 mole percent, 5 mole percent. These are and also that you put in the very high scale like the 1 kg or 2 kg, then in that cases also you can recover your palladium, that's metal also that you can so sometimes it is also possible to recover also, because after that the whole reaction, then you will get your palladium also. So like in some reaction that you can recover also, but that's where we will perform the reaction in small scale. So we generally don't that recover that the metal, but in industrial cases that it is very the important to recover, that if you recover then you will get your metal also, and you will get your product that without affecting any other things. So because this metal like palladium, that iridium, ruthenium, these are high price, these metal complexes are. So and these metal complexes are that these are in air, these are air sensitive, so in the, it will oxidize by air also. So as we have to use all this metal in the argon atmosphere, like in glove box or that argon atmosphere, that you should be very careful. Okay, you have any problem? In- no. Okay. Yes. Then in the next question we have to see, so we have that. Yes. Oh, then options are wrong. I think that oxygen that I have. You just ignore the option, okay? Because sometimes whatever the slide I have made, that's before 2 years old. I'm not checking that the slides options, but I'm checking only that whatever on that slides whether it is correct or not. That's whatever that the reaction pathway. The option that you can ignore sometimes, okay? Because sometimes I make that the question, so I forgot to add some options. Okay, then I will change that option. But when I provide uh, the slides, in that cases, what will happen? So you have that the palladium also palladium 3 and sodium hydroxide and acidic after that. Anything? Yeah, do you have any idea, anything? Then what will happen in the first step? Yeah. Ah, then yeah, this is a we call them as the first step what will happen, whatever that this one is nothing but a boronate ester in this one. This one is nothing but a boronate ester. This part is nothing that you just ignore, but whatever that is of palladium and the boronate ester and iodine, that's whatever the RL halide. Yeah, it will undergo a coupling. And this coupling we call them as like boronic acid and boronate ester also. That's if you use any RL halides like bromides and iodide also, the influence of palladium and base, then you will get your corresponding that Suzuki coupling product. So whatever the product, this one is our that the Suzuki coupling product. And you will get, and your whatever that the alkene, that stereochemistry, yeah, that will be same after that the coupling product also. That is the most important thing. In that whole reaction, you just see the coupling, the stereochemistry of alkyne, sorry, that alkene, in that whole reaction, whatever the stereochemistry of boronate ester, that will be same in your product also after coupling. Okay, this one is the most important things in Suzuki coupling. You have to be very careful. And after that, we have used that acidic workup. Sorry, that the acidic condition, that's one. For that, that the deprotection of our this one enol ether. That this one is nothing but enol ether to deprotect to their corresponding aldehyde. That if it is nothing but enol, and after that it will convert it to their corresponding aldehyde. And after what will happen? That's we are using the acidic sources, whatever the acidic sources, that will also activate our aldehyde, and whatever our NH, the nucleophile, that nitrogen lone pair, that will be attacked to our keto groups, whatever carbonyl group, and we will get our corresponding, after that the elimination of water group, we will get our corresponding indole, that the three substituted indole, 3 and that nitrogen substituted indole group will get. And that's the whole reaction. Actually, what will happen? From that, the 2-iodo, is whatever our that iodine part, with that, it is nothing but a, as you call it, that the 2-iodo-aniline derivative. In that case, the aniline that will be derivated by the carboxylic group, that the ketone groups in it, and we have the boronate ester. And in the first case, the coupling reaction will happen, and we have after that, the hydrolysis of that enol ether, who will get our corresponding keto groups. And that keto group also will be activated by our acid group, and we will get our corresponding that indole product in the whole reaction. By using this method also, that you can synthesize that some different kind of indole that's if you that's need. Suppose that if you have any very bulky group in that, like that if you have derivatives of that the 3 to 4, that's this kind of rig, then in that cases particularly that you will get your that you can get your indole group was the synthesis of your indole moiety, the second synthesis through this process also, that it is be possible. So that's when it will generally that's we have that Fischer indole synthesis, everything we have there for indole synthesis, but for some complicated kinds of indole we have to be synthesized, that we need to follow this kind of procedure also. That's when you have only need some particular kind of that can be possible by in the other method. In that cases, this method also will help to get your corresponding indole product. Okay. Yeah. In that the next questions we have, just say that we have alkyne, but in that cases we have deuterated alkyne. That the deuterated alkyne, and along with our that the boron ester. That's whatever that the boron esters. That's boron we have. This one you just see. This is a boron. But in that first cases, you just see in the previous cases we have used palladium metal. That's whatever the palladium metal. But in that cases we don't have used that any palladium metal in this case. And what will happen actually? In this case, in the first step, what will actually happen? Yeah, then what will happen? That this reaction we call them as no. That's whatever that the fast case. How that's it. Whatever that this one is nothing but a borate. The borane addition to our corresponding alkyl. This one is nothing but a borane. You just see this one is nothing but a borane. Borane. Huh. Only hydrogen reaction with alkyl. The terminal alkyl and selectivity also will happen. That's because we are not using any kind of that's because they as metals. That's why there is no possibility of any coupling product will be happen. So first case actually what will happen? That will it will undergoes a that the radioselective hydroboration reaction. That's whatever that the deuterated because in that cases that boron and deuterated will be there. That's why it will reacts in such a way that for the less steric in that and whatever that the boron and deuterium that will be comes from that the same phases only. That's why as you will get it because in that cases also we have deuterated. That's why you will get a transfer. But suppose that if you have that the deuterated here, then you will get sorry. In that cases, if you have hydrogen, then you will get your corresponding hydrogen also. And in that cases, if you have hydrogen, then you will get your hydrogen here whatever that this hydrogen or this boron that will be comes from this boron reagents only and whatever that the pH and hydrogen that will be this deuterium that will comes from this alkyl. That's why you will get a radioselective. That's whatever I already explained in boron chemistry. That's whatever the alkyl and alkane cases whatever your addition that will be occurs from that the same phases like we call them as syn addition. This is only why because that the addition of the alkene and alkyne to their corresponding boron it is a concerted manner. That's why it always occurs from that the same phases only. That's whatever the boron and hydrogen that has to be comes from same phases only. Okay, and it also has to comes from that whatever that the boron if you have that if of unsymmetrical boron that in that particular cases that you will get a as boron as that the most that the most stable boron like in that case because of steric index only that's why this boron it won't comes to that the this carbon that instead of this carbon that it comes to that this carbon that's why we in this case also stereochemistry also matter the stereochemistry and also radioselectivity and these are nothing but after that the acidic workup that you will hydrolyze your boronate ester and you will get your corresponding boronic acid. These are we call them as a precursor. That this step is as a precursor for the synthesis of boronic acid. That we can synthesize that boronic acid from the alkyne and with boron and followed by the boronate ester and followed by that the we call them acidic workup and you will get your corresponding that boronic acid. These are that the precursor that how to synthesize your corresponding boronic acid. And after that only we can do that different kind of coupling projects with the different kind of the reagents. Yeah, I'll check whether that recording will be there or not. Okay. How much time is already? Then after that what will happen? In the first step, huh, yeah, we'll get that the coupling will be happen. That. But what will be that the stereochemistry of that the coupling product? Because we have that the Z that alkene. You just see this one is nothing but our this one is nothing but our Z alkene. Okay. Then whatever our borrowing is yeah, that will after that coupling product whether we'll get that whatever the bond between this carbon and this carbon. It will be for the bond between this carbon and this carbon that will whether there's a bond that sorry the whatever that the group of that alkene with that phenyl group yeah that will form that cis 2 r phenyl group or the other trans 2 r phenyl group after that coupling product you know no that it will comes as a cis whatever that the stereochemistry of that's iodides in that alkene what structure meter after the coupling product you will get the stereochemistry of this boronic acid also and also your iodide that will be same that the starting metal and that the product. Okay, in that the whole mechanism of that the Suzuki coupling, there is no change of the year stereochemistry during whole that the year coupling reaction that the catalytic cycle. Okay, in that the whole catalyst cycle, there is no stereochemistry, no change in that the stereochemistry of that either your aryl halides or that your boronate ester in that the whole reacts. So be careful. So stereochemistry also may be important, but that in the cases you have the other two that option also that you just see. This one is that the cis one, and another one is also that trans one also will be there. So that you have to be careful which one will be your that the product. Okay. So do you have any questions? Let's prefer from that in this slides until. No. Okay. Yeah. In that cases, what will happen? Is yeah. In that first cases, the alkylation will happen after that. Yes. Okay. Then go to that. Yeah. That's what about the inhalation one. Yeah, good. And maybe we know two things. What actually happened? These are options that we just ignore. Water from the LDA that will get our corresponding enolates. That the lithium enolate will get. And after what will happen, we have allyl bromides. And that allyl bromide that will be react to that the carbon substitution will be happen over the inlet. The inlet will attack to their corresponding allyl bromide and we will get our corresponding the allyl substituted product. The whatever the allyl substituted product will get. And after that, what will happen? That in presence of palladium dichlorides and in that oxygen, that oxygen also most important thing for that oxidation. The oxygen we have to need and copper chloride, DMF, everything that we have to be need for that whole catalytic that the reaction. Whatever that from that alkene, that you will get your corresponding that ketone product by using that the Walker oxidation. And this reaction we call them as Walker oxidation reaction. Okay. And after that, what will happen? That we have base, and there is possibility of that this proton and this person both proton will be the enolite, but this one that will be favorable because of for the further kind of reaction. Because if it is from the enolite from this one, then there is no other possible for that. We call them as cyclation with this keto won't be possible. That's why if you want to go to the other the another kind of that this methyl group from that methyl group it will take proton because in this case this proton and this proton they don't have does not that much that acidic gap between both one. But in that case because of that the further reaction of the ring favorability of that 5 member ring, that's why that's inhaled will be it's not inhaled the inhaled anion, that's whatever the anion will be formed, and after that the nucleophilic attack from this carbon to this keto group will be happen and you will get your corresponding that alpha, it's not alpha, it we call them as alpha beta gamma, that gamma bicyclic that the hydroxy ketone you will get, and after that elimination will happen and you will get your corresponding alkene product. That's why we won't get this alkene that the more substituted alkene that instead of that the less substituted alkene we got. Yeah, my question is that why we got this alkene in this because in this particular case this hydrogen also will be there, and there is chances that the elimination will happens in the ring junction, then only we'll get our more substituted alkene, but in that cases we'll get you just see that the product will get as a the less substituted one. Yes or no? Then why no? Yeah, these are only because of the stability of the carbonyl groups. That's if it is formed in that conjugation, then you get the your conjugation with your carbonyl. That's why this is more stable as compared to if your alkene that will be present as alone. That alkene that will undergoes with that the conjugation with our carbonyl group. That because of the carbonyl group, your alkene will be stabilized by a carbonyl. That's why we call them as tri-substituted alkene will be formed as compared to our and the tetra-substituted alkene. Okay. Do you know that the mechanism of that's we call them as yeah, then, yeah, these are the normal mechanism of from the alkene to our corresponding ketone and how we'll get the corresponding ketone. You always get a ketone. Okay. The always get a ketone. That if you have that the monosubstituted alkene, then you will get always a ketone. That's from that palladium and what is the role because first it will happen. That's whatever the alkene that will bind to the palladium, then it undergoes a ligand exchange reaction. So that's and one chlorine group will be removed and your that's alkene that will be coordinated to a corresponding palladium. And after that, whatever the water, yeah, that will also replace another the chlorine group. After that, what will happen? That's whatever that the water again also that it undergoes a the Markovnikov the addition reaction to that alkene, and you will get a corresponding alcohol. That the palladium the complex alcohol you will get, and in that whatever the complex this complex it will remove that one chlorine group, and that's it. This step we call them as the redeterministic step. And after that, from that we call them as a beta hydride elimination reaction will happen, and you will get a corresponding alkene. So whatever that the this palladium complex, it undergoes a beta hydride elimination reaction, and after that, whatever your product is whatever they say, enone that you will convert it to their corresponding ketone product. After the isomerization, you will get your corresponding. We join. Okay, sorry, but that's some network interruption will be there. So okay, no, yeah, my network will be because that's what I'm using that LAN. That's whatever the other router LAN. So because we are using that's our institute the LAN connection. So after some time it will be disconnected. After that 1 hour, 2 hour, that we have to be log in again from our corresponding. That's whatever the ID have. Sometime it will happen. So okay. Mm. So whatever that the mechanism, that first it will undergoes a Markovnikov addition reaction, and after that, that the beta hydride elimination, and we will get our corresponding that ketone product from our alkane. And in the all cases, that all the stick is needed. That whatever the oxygen that we need for that the oxidation of our the copper chlorides also. The is that the mechanism? Okay. The next questions we have, you just see, I will say that in that next questions, that's we have. You just try to because and the stereochemistry also you have to but before that the stereochemistry first you just try to solve that the which product will get. And how that the reactor will proceeds. Yes. No. So whatever the palladium metal will what will happen. So whatever you are saying that the palladium metal has there is some role also. You just see, yeah, that's whatever that's after that's so we'll get a product. What actually happened? That's whatever the palladium. Okay, if this come, then that's if of any kinds of that allylic alcohol or that the allylic alcohol or allylic acetate or in that instead of acetyl group that if of any kinds the other kind of living group that if you have also, then this living group that will be replaced with the palladium and you will get a that the pi allyl. That's whatever this one is nothing but a pi allyl complex. That's whatever. Okay. This one is palladium, that the pi allyl complex you will get. That by using that the palladium. Don't. This is nothing but a allyl complex. Okay. That after the binding of the palladium. And after the what will happen? That here. That if you have two sides, that the which sides that it will be attacked, that one side is more sterically hinders and another side is the less sterically hinders. And you will get your corresponding attack from this position and you will get your corresponding that cyclase product. Whatever that product will get. Okay, because of this palladium only, this one will be happen. The palladium and phosphate. Because as palladium acetate and that phosphate that will be react and after the acidic group will remove, then it will form a palladium zero species and that palladium zero species it will bind with our allylic alcohol and it will remove our acetate group. And whatever the other triethylamine we are using, this triethylamine will help the deprotonated our nitrogen proton and after that your cyclation will be happy. But why that the stereochemistry will be cis? That's why now others. This is only because that whatever that the palladium, this palladium, okay, that it will bind with that the how that's to think whether that whatever that the pi allyl complex whatever that will be formed, whether it will be formed from that the same side of the of our allyl complex or the other sides of our the allyl complex. What do you think? Yeah, because whatever that the what actually happened because of that the steric index only it will form from that whatever the palladium it will bind that the opposite of that the acetyl group. After that only your acetyl group will remove. That's why first it will happen one inverse. Okay, first one inverse will happen. After that whatever that the palladium complex will be formed. After the first in the first case there is one SN2 mechanism, okay, but after that when there is will be then another the nucleophilic attack, then there is another SN2 reaction that in that whole reaction what will actually happen, there is no change in stereochemistry after that the cyclization also, but in that reaction what will actually happen, first it will undergo one inversion, after that it also that it also undergoes another inversion reaction. That's why we call them as in the whole reaction there is no change in stereochemistry. That you can say because after that after two inversions, then it will get to their same stereochemistry after that the reaction also. That's why that if you attacks, suppose if you don't use any that palladium and if you substituted by using any strong bases and it will deprotonate this nitrogen and it will attack to this carbon and here through we call them as through SN2 reaction, that's your acetyl group will remove. But whatever that the attack will happens from that the below phases. But in this particular case, by using palladium and phosphine, and in that particular cases, your attack will happen from that the above phases. And that's why you will get your ring junction as a cis phase. But if you don't use that palladium, then your attack will be happens from that the below phases only. Understand? Yeah. That's huh. No, whatever that if you don't use palladium, then what will actually happen? Then it only undergoes that we call them as SN2 reactions only. That this nitrogen that will be attacked to this carbon. Yes or no? Huh. That SN2 reaction only. Then in that particular cases, only one inversion will happen. Then only you will get here that the whatever the stereochemistry of the product will get that the reverse one, that the trans one will get, because in that case we will get cis one, but in that case we will get a trans one. But because of that palladium only, yes, yeah, yeah, definitely. Because after that SN2 reaction, the stereochemistry in that in SN2 reaction, what will happen? The stereochemistry of that carbon cell will be inversion will be happen. But in that case, what will actually happen? Thus, it undergoes a two inversion. That's why in the whole reaction there is no change in stereochemistry. Thus, we can say like that. But there is change in stereochemistry in the first step also during formation of pi allele complex, and after that the nucleophilic attack also in that will happen. In that cases, that another kind of inversion will be happen. That's why we'll get a corresponding that the no inversion product will get. Okay. Yeah, still that you have any doubt? Okay. And this is that this reaction will develop by that's our Professor Barry M. Trost. Now also that this group also working on that the palladium metal, and very trust that the professor he already published that 1000 publication in chemistry journal. So these are very great achievement till nowadays also that to publish that the 1000 year journal paper in a reputed the journal. And that Chisuji also actually help also for that the discovery of this coupling reaction. Actually, what will happen? Just whatever here that this allylic halides or that allylic acetate, the instead of X, it is nothing but the acetate or the OR group that will contain a living group. That it will happen the coordination with our palladium one, palladium zero. Yeah, that will be our that we call them as 16 electron species, and that's 16 the electron places of that palladium that will be that the more reactive towards that's any alkene for their coordination reaction. Okay. And in that case, what actually happens that it undergoes a the oxidation reaction, and it will form a pi allele complex. With that it will form a pi allele complex. This pi allele palladium and intermediate will be happen. And after that, the if you have nucleophile, then there is chances of that the nucleophile this nucleophile it will be attacked to that this position also and this position also. That both position will be possible, but most of the time it will be attacked at the other terminal one. This is only why because of the other stereochemistry that the steric hindrance only. But the stereochemistry of that that will be depend upon that the from which phases your pi allyl that intermediate complex will be formed. In that opposite phases, that's your attack will be happen. Okay, yeah, and through that the after that the attack will be happen, and after the reductive we call them as elimination reaction, and you will get your corresponding that coupling product, and along with that's whatever that your palladium also you will get as such. This is the other general mechanism. And in the next questions, that's that instead of that palladium metal, we are using that the Grob catalyst. Okay, that the ruthenium metal. That the Grob catalyst, maybe you know that's the first generation of Grob catalyst, second generation, that the third generation of the Grob catalyst will be there. In that case, we are using that the Grob's catalyst, and along with that the DC solvent also. And after that, we have lithium aluminum hydride. Okay, first you just decide that's whether which product will be for. Yeah, I'll take a 2 to 3 minutes leave for water. Okay, you can try to solve. Yeah, what will happen? Yeah, then we call them as which reaction? The ring closing metathesis. Okay, the ring closing or the ring opening sometimes also that metathesis reaction. Do you know that how the mechanism will happens with the group at least? Mechanism will you know? Okay. Yeah, I will show in the next slides also the mechanism. Actually, what will happen? That's whatever the one group catalyst. Yeah, that will bind with our one of the alkene, and you will get that the four member that this is nothing but a the you call them as a group catalyst. Okay, that that instead of that this phosphine that the phosphine that cyclohexane that tricyclohexane that we have different kind of that we call them as first generation, second generation, and third generation. The different kind of aluminum catalyst also will be there. Okay, if you use then you will it will get com- that the four member rings. That's whatever with that the ruthenium complex, and after that what will happen that in that particular case it will remove this R, and that through that the alkyne, that's whatever the alkene will be removed, and after that it will form a that we call them as a precursor of that the Groves catalyst. And whatever the Groves catalyst of the R group, that will be again from with the or by reacts with our Groves catalyst with our that one of the alkane, and after that whatever that the alkene and that this that the ruthenium that we call them as it is nothing but that one type of carbon, and that will be reacts with our do you know that whatever that the ruthenium and that rhodium that whatever the catalyst, these are we call them as a carbenoid. Okay, these are nothing but a carbenoid catalyst. And this carbenoid uh, yeah, that will be we call that undergoes a cyclation or reacts with our the you call it another alkene, and you will get here corresponding that this four member ring to with that the ruthenium, and after that the elimination you will get a corresponding that six member ring will be formed. That is member that we call them as a lactam. That the four and five member that both bicyclic lactam you will get through that the whole we call them as a ring closing metathesis reaction that in play with the help of Grob catalyst. And after that we are using lithium aluminum hydride. Then what will happen? That we have different kind of functional group. Then which functional groups will be reduced by lithium aluminum hydride? Keto. Whether this one is keto or what? Yeah, this amide group will be reduced to their corresponding that alcohol you will get. Okay. Yeah, this one is because I'm not writing in that case, but this keto group just whatever the cyclic amide that will be reduced. Okay, this option will be not there because I am not attaching that one, or maybe that in that during that making the slides also maybe it will be erased. Okay, after that it will be reduced by the lithium aluminum hydride, and you will get and whatever that we have alkane, it won't be reduced by lithium aluminum hydride. The normal alkane it won't be reduced, and the general mechanism for that the closing method thesis is that is nothing but whatever that's your dialkane. Yeah, that will reacts with your graph catalyst through that this mechanism, and you will get after that the ring closing metathesis also that you will get your the cyclase product, and along with also the byproduct in that the whole reaction will get as a the byproduct in the during that the ring closing metathesis reaction. Yeah, that's ethylene gas will be formed, and that's the gas in that the reaction only that it will evaporate. Okay, so yeah, that will be the easier we call them as the easiest to remove. That's your byproduct in that the reaction. Because if you got that's any gaseous byproduct, then that will be very easy to remove in that from a reaction mixture. That if you get that any liquid or solid, then it will be very difficult to remove. That first you have to distillation that or that you get that liquid or that you have to do that purification, that the different kind of purification method to purify a product. But suppose that if you get a byproduct as a gas, then it will evaporate, and you no need to do any kind of separation. But your starting metal is also a, that's the whatever the product you will get a gas also. That's whatever that the product you will expect, that you will get a that your major product as a gas, and also that your byproduct also a gas. Then in that case particularly it will be difficult. But in that most of the organic reaction, that during that when that we are using the graph catalyst, that's whatever the most of the almost more than 99%, that you will get as a LG product as a liquid or solid, that whatever you will get. You won't get as the product as a as gaseous product. But whatever that the byproduct you will get as a gaseous. That's why these are very easiest to remove in the whole reaction. That's why these are so, and there's a lot of application for that, this kind of cyclation, that you can use that the more dialkene to your corresponding, that the intermolecular or also the intermolecular will be happen. And these are for this only, that's Groves got that the Nobel Prize for the discovery of that the metathesis reaction. And that's whatever that also in that cases in your that sometimes that the molybdenum, we call them uh, molybdenum, or as whatever that the ruthenium also, that as compared to that the ruthenium and molybdenum, both will be that's we call them as both carbenoid. That will be also possible that undergoes a ring closing metathesis reactions also. That instead of that ruthenium that we have read, but later that some people they have change your so whatever a complex from the ruthenium to that the some they have used that the molybdenum based growth catalyst also, that will be also possible. But the base, that's the people they have used, and that's we call them as ruthenium based. That's whatever that the discovered by Groves. From that from the name of that the scientist, that we got their name as a Groves catalyst. Okay. Do you have still any doubts? Okay. In that cases, then what will happen? That's in that you have to be always very careful. Okay, and the which kinds of that's your metal will be there, because that after reading a lot of reaction of palladium coupling and the other kind of coupling, then you will get some confusion also. So that's why to get that the every kind of laser selectivity, stereo selectivity, that you have to be very careful about which kind of reagent they have used. That will be that the most important things to understand, to identify that the reaction. Maybe that you can know that this reaction it will undergo a coupling reaction. That's okay. But all the reaction, if you know, then if someone will give a very complex moiety, and if you have very different kind of functional group, or also then in that particular cases, that you can find out that the at which particular functional group that it will be reacts. Then what will happen in that cases? Hi. Yes. Yeah, this is that the product will get. Okay. But how that will get this product, that you have to be explained. This reaction we call them as Hague reaction. Okay. And the Hague coupling reaction. And these are nothing but a generally Hague coupling is nothing but that if you have any RL halides, or if you have any that the carbon sp2 halides, or that's if you, the coupling between carbon sp2 halides and alkene. That is this one. This alkene and that our RL high, that will undergo the Hague coupling reaction, the in presence of palladium, acetate, and phosphine and silver carbonate. Yes, no, that will be see that the mechanism also. Okay, don't worry. That I will explain that why that will get that this alkene. Okay, because the mechanism also in that Hague reaction, the stereochemistry that will be comes from that the mechanism only. And this thing that you should be always careful that the which one who will get, because the whatever that alkene will be formed, that's in that after that last step, that will that alkene formed from that the we call them as step, we call them as syn beta hydride elimination. Okay, whatever that the palladium and your stereochemistry of your hydrogen, that will be has to be set. Then only in that particular cases, that instead of that the conjugated one, that's we still got our major product as a, we call them as that the uh, we call them as unconjugated or something that we call, I don't know that the term about, but that, but if it is comes from that the same cases, in that whole cases, the mechanism actually what will happen, that first it undergoes an oxidative addition with our palladium, because whatever the palladium acetate and our phosphate, that will be react, and you will get that the removal of acetate group, and you will get your corresponding palladium PPH2 whole 2, that that palladium zero complex. Okay, and that zero complex, that will be undergoes the oxidative addition reaction with our halide, and you will get your corresponding oxidative additive product. And after that, what will happen, that it will react with, that's whatever that the palladium and iodide, that's what it will reacts with our this alkene through a cis insertion reaction. That's whatever that this bond and whatever your palladium bond. First, you have to understand this bond and whatever your palladium bond. This both bond, that it undergoes through a syn insertion reaction. Syn insertion, whatever that your bond will be formed, and after that, whatever that the palladium, the stereochemistry of both the add has to be set. Understand? This stereochemistry. That's be careful, okay? And after that, what will happen? Okay, sorry. After that, in the all cases, that it undergoes a syn beta hydrate elimination reaction. And in that cases, we have two different kind of hydrogen, this hydrogen and this hydrogen. But in this carbon also, there is another the hydrogen also, yeah, that will belongs to that the above sides also. But in that particular case, that we have hydrogen, that will be from that the below sides only. That, sorry, that the which sides only, that the above sides. But still, that's we have that palladium from that the below side. But that's why it can undergo a that a syn hydrogen elimination with this hydrogen, because the stereochemistry of that the both palladium and hydrogen, uh, is we call them as a trans, but on that the other carbon we have that hydrogen, that will be we call them as same stereochemistry with our palladium. That's why it undergoes a that is syn beta hydrogen elimination with this hydrogen, and you will get your corresponding alkene here, that instead of here. Okay, then do you understand? That's no. Okay, that most that the important things in it, hair coupling it, that the syn insertion will be happen. That's whatever that the after oxidative addition, the mechanism is most important in hair coupling. Okay, so whatever that after that the oxidative addition of palladium with our RL halide, and it reacts with that the alkene, that's a coupling partner with it. The syn insertion reaction. First, it will undergo a syn insertion reaction, and after that also that it will undergo a syn hydrate elimination reaction, and you will get your corresponding alkene product. That syn hydrate elimination and syn insertion reaction, that will be more important. That your whole reaction of hair coupling product. Okay. Do you have any doubt? No. Okay. Okay. Also, that we'll see that there's some titanium reagent also. Yeah. What will happen in the reaction? Yeah. Hmm. After that, huh? Do you know what is this reagent? Yes, sir. You don't know the name of this reagent? I think you should know. Yes? No. say titanium based reagent. Maybe you know there is some reaction, that Tibbe reaction. Tibbe reagent. It's not Tibbe, Tebbe. That's some people they have used the other Tebbe. Tebbe. You don't know the Tibbe reagents. That the cyclopentane, that the dicyclopentane titanium. That's we call them as aluminum chlorides. That dimethyl aluminum chloride complex, and these are nothing but we call them as that's that the titanium base, that's the carbenoid, and that will be reacts with our ketone, ester, that's any kind of carbonyl group like ester also, that it can be possible to convert their corresponding alkene. That's in Wittig reaction that we can convert only, that's our keto to their corresponding alkene. Okay, or our aldehyde to their corresponding alkene. But in PV, by using that titanium one, you can convert your that we call them as, wait 1 minute, sir. That we can convert our ester group to their corresponding alkene also. Yeah, that is that the good thing about TBS reaction. But in the Wittig reaction, that we can only convert our keto and the aldehyde group to their corresponding mono disubstituted alkane. In the whole reaction, what will actually happen? That's whatever first, it will undergoes the protection of ketone, the in presence of the 1,2-diol, and also the paratoluene sulfonic acid. The protection of the ketone will be happen. After that, whatever the Tebe reagent we are using, that will converts our. If you don't protect, then it will undergoes react with our keto first. Then only after that it will react with our ester. But it will react with that the ester also. But if you use only that, in that particular case, if you use that's we call them Wittig salt, then you will get only that the your from that keto to your corresponding alkene, that you will get that if you use Wittig salt. But if you use TVS reagent, that both keto and ester both will be converted to their corresponding alkene group. There is no that role of, sorry, there is no role of that this OMe or that other group. It always that converts our keto to their corresponding alkene. Okay, and in this particular cases, you always get that the terminal alkene. You just see that always that by using TB reagent, that you always get a terminal alkene group. That is the most important things in the reaction. But in Wittig salt, that if you use that the different kind of that the Wittig salt, then you will get a substituted that the Z alkene. In that cases, that if you use stabilize or the, but in that cases that you will get a terminal alkene. That this one, that you will get a, we call them as that the exoalkene. That instead of endoalkene, because endoalkene is more stable, but still you will get a exoalkene. And this reaction we call them as that the homologation reaction. That you will get a that the one carbon mole. Because whatever the carbenoid, that will be reacts with our keto groups or the carbonyl group, and you will get a corresponding that hey, this particular cases that we don't have that the keto group, because in the first case we have protected. Then what will actually happen, that you will get a corresponding that alkene from this ester to that you will get a that the enol ether. That's whatever the ester, after the previous reaction you will get a corresponding enol ether. Okay. And after that, what will happen? That's we have hydrolysis. Then what will happen from the hydrolysis, that you can hydrolyze here that this group, and along with also that's that if you use that the strong that the dehydrating agent, then here this first that it will hydrolyze this we call them as enol ether group, and also that's whatever that's keto group that will be protected. It also that hydrolyze with that the acidic workup, and you will get a corresponding keto product. Okay, this is nothing but the protection one. This one has to be after that reaction. It also undergoes that we call them as deprotection, and you will get a corresponding keto groups. Okay, and this is our nothing but the correct option for that C. C is nothing but from this one, that after that deprotection of your that this diacetyl, that you will get your corresponding keto products. That in the whole reaction, actually what will happen from that ester, that's you can convert to their corresponding keto group. In the whole reaction, there is nothing will be changed. From a ester to you will get your corresponding keto. Yes or no? In that whole reaction, what will actually happen? The conversion you have to be seen. The conversion from that in the whole reaction by using TPC reagent. But that you can convert from that if you use any that the reducing agent or the other kind of reagent, then you can that's convert that ester to that the keto groups. But your reaction won't stop at keto groups because when it will form keto, then it will further react with that the reducing agent and you will get a corresponding alcohol. Okay, because that the yes. Suppose that if you have any that the WinRAM amide, that's from the WinRAM amide, if you give that the Grignard reagent or organolithium, that you can convert to their corresponding ketone. Yeah, that can be possible. But from that ester group, that it won't be possible. Okay, from ester group that you can convert it. From ester to it also possible, but the first the reaction condition for that the reaction that we are using, first you have to use that the isopropyl magnesium chlorides that these are for the research basis. Maybe you don't know or don't know. I don't know. First, you have to use, and that's we call them as isopropyl magnesium bromides. And after that, it will form you call them as after that you have to use that that's whatever that the WinRAM amide that you have to synthesize that you can synthesize from ester to their corresponding that WinRAM amide through that's whatever that's from ester to that you can convert it to their corresponding WinRAM amide by using that the organomagnesium chlorides and along with your WinRAM that salt with a base that normally diisopropylamine or triethylamine also you can use. And after that, from WinRAM amide only that you can convert it to that keto, that's whatever the WinRAM amide to their corresponding keto. Or in all other cases, you can convert it. Then it will be converted to their corresponding their alcohol group. In the all cases, that if you use ester or the other cases, yeah, that will be converted to their corresponding ester group. Okay. And in that the next slides we have that's the last questions. This is my that the last slides of that today classes. Okay. So already I think 1 6. Okay. Just see that we have that butene, that the methyl substituted butene, sorry, butadiene, and we have that the nitroalkene that represents yes, which reaction? Really? Yeah, magmatic that coupling reaction it will be happens with that the titanium chloride that in presence of keto, keto. But then what will happen in that cases? First you just see. First actually what will happen? These are not. That's whatever that magmatic coupling is something different. That's whatever that two keto group that will be coupled that in presence of titanium with some reducing agent like zinc or that other kind of mercury or that some other kind of reducing agent that you can couple between the two alkene, sorry, keto to their corresponding alkene. But in that case, what will actually happen? That it undergoes whatever that this one is nothing but diene and this one is nothing but a dienophile. And this diene is electron rich and this dienophile is we call it electron deficient because of that the minus m the character of our nitro group. That's why it will activate our alkene that with this dienophile and also that will be reacts with our diene. It undergoes a 2 plus 4 plus 2 cycloaddition reaction that in presence of air. Then you will get a corresponding that keto. So sorry, that the nitro product. After that the six membering formation. Do you know that the this 4 plus 2 cycloaddition reaction we call them as which reaction? Yeah, it is nothing but that the this alder reaction. That's why it is and these alder reaction are we call them as concerted reaction. The concerted reaction these are, and the formation of the six-member ring that you will get. And after that, what will happen from this nitro to the, that's we have a that no nothing but we call them as aliphatic that nitro group. After that, we have the titanium chlorides and hydrochloric acid. Then what will happen? Keto. Then what is that the name of this reaction? Hmm? Yeah, this reaction we call them as NEP reaction. Whatever the McMurray coupling that you are saying, that is in that cases also people use that the titanium. But in that case, the functional group that who have to be look for that a keto, and that keto that will be reacts with that the different keto or that a safe that we call the self keto also through radical cyclation reaction, and after that elimination, then you will get different product that either diol or that your corresponding alkene. Most of the time you will get your corresponding transalkene because of that your reaction will proceed through that radical intermediate. That's why you will get more stable alkene product in McMurray coupling. Okay. In that particular cases, we have that's whatever that you are saying that titanium trichloride and DME two, and that's we are using that the reducing agent also some that the zinc copper and DME also. This reaction we call them as McMurray coupling because in that particular cases we have dialdehyde. Yes or no? Yeah, this condition is nothing but that the name reaction, but this condition is only for that the McMurray coupling, and this this undergoes through that the first it will form that the diol, and if you gives how the mechanism will be happen. Sorry, that that's whatever that the titanium chloride that it will donate that the electron and it will form a that the both carbonyl group, and it will form a that the diradical anion, and after that this diradical anion, yeah, that will be reacts with that the that the coupling reacts with coupling, and you will get that the carbon carbon bond formation will be happen, and after that that protonation will be happen, and you will get a diol, and also from the diol also it can be cleavage to their corresponding alkene also sometimes. Now, it will be different that the whether that you are using that the reaction condition as a room temperature or heating, that will be depends that whether that your reaction will stop at diol or also that's up to that the alkene. If you have the more heating condition, then it will be converted from the diol to the corresponding alkene, or if you don't have, then in that particular case this the dialdehyde, after that the coupling reaction, and the couple between both dialdehyde, then you will get your corresponding diol product. Okay, and this reaction we call them as McMurray coupling reaction. These two question is nothing but that's from the titanium base reagent. Okay, today for that uh, this whatever that we have discussed, that the most of the question is related about palladium and titanium and ruthenium also that we have seen. In titanium we have seen that three name reaction. One is name reaction, the another one is uh, McMurray coupling, and that another one, the third one is nothing but the Tiveri reagent. These are the three name reaction that will be based on the titanium reagents. And that in palladium that we have seen that Hay coupling, Suzuki coupling, that pi allele how that the pi allele complex will be happen, and their stereochemistry of the whole reaction. And also we have seen that the Grove catalyst also, how that Grove catalyst will react with alkene, that the ring closing metathesis reaction and their byproducts as a that the ethylene molecule also. Okay, do you have any doubt for the whole classes? That I am done for today, that I have completed whatever the slides we have. Okay, the Shakti lab, do you have any doubt? Because oh, okay. Okay. Yeah, do you have any problem related about assessment or that anything? Because we have to. No, okay. Okay. Okay, thank you for joining. Thank you both. Okay, good night.